Okay, today is June 16th, and we would like to go with this material on how the shear stress distribution produces a redistribution in normal stress, and at the end, this redistribution of normal stress is the origin of the necessity of the concept of effective breath. Okay, so even the deck of the ship is at the same distance from the neutral axis, right? So you were supposed to have a constant, a uniform normal stress on the deck, but it's not. Why not? Because there is the shear causes some redistribution, especially in the areas, okay, on the deck close to the vertical sides or the longitudinal bulkheads. That's typical, right? And because of that, of course, we're interested in the larger values, largest values. We have to check that's below the allowable value of the stress. And that's the reason why we presented the concept of effective breath last Tuesday. Now, we're going to go into more of these details, right? How this shear produces a redistribution of normal stress. And we're going to present a theory. It's a very old theory from an engineer called Taylor, right? There. And we're going to complete with an example. The simplest example is if we apply all of this in the case of a flat bar, okay? So that's something like this. So it's just one single rectangle, and that's it. And then at the end of the session, I'm going to give some 10-15 minutes to say a little bit more about how to complete the assignment, okay, about the report of the experimental results, okay? So that's the agenda for today. Is there any other questions? Yes, you can raise your hand and let me know, especially at the end of the session, okay? So let's start. Okay, see. Niela, would you please confirm me that you can see my full screen?
Yes, doctor.
Okay, thank you. So, so we're going to, you see, I explained to you that because you need the concept of effective breath, I changed the order of presentation of this material. So last Tuesday, I presented 2.4, and now I'm going to go with 2.3, okay? So let's go on. Let's include here the date. Today is June 16th. So it's June 16th. Okay, so we're going to say how to, we're going to explain how to calculate the axial distortion of the beam section, okay? Right now, okay, if you have a transverse section, that's x-axis, that's your section. According to pure bending, what this section does is moves vertically and rotates, okay? Moves vertically and rotates. If you have another section here, the two sections move vertically and they rotate. It is possible they don't rotate the same amount, but they keep straight. That's what we call the kinematic hypothesis. Okay, today we're going to admit that this section moves vertically, rotates, but also there's going to be some distortion, okay? The axial motion, this is axis, is not going to be just that. It's going to be something extra, and that's because we have shear stress, and we are going to consider that. So we cannot neglect the effect of a shear stress. That's the origin of this point. Okay, so we have this relation, Miss Jurado. Do you know where this expression comes from? From where we get this expression? Gamma equal du dy plus dv dx, and is equal to tau divided by g. Do you know, do you recall this expression from where we get this, Miss Jurado? No, it's not here, Miss Jurado? Miss Jurado? She tried to turn on. Okay, let's see somebody else. Mr. Gomez, do you remember from where do you get this expression?
Good morning, doctor.
Do you know? Do you remember from where do we get this expression? This is gamma, this is tau, and g. Mr. Chiriboga, do you remember from where we get this expression?
The integration of the area, no?
No. Mr. Hidrobo, do you remember?
Is the Excel?
I'm not Mr. I am doctor, I am a professor, I'm an engineer. See, the reason I don't like to be called Mr. is because Mr., that's the term that you use in high school. And what I want from you is to recognize that you are not in high school anymore. And here you are adults and you're supposed to be responsible for your acts. Okay, that's the reason why I don't like to be called Mr. Okay, go on, please.
Hooke's law.
Exactly, Hooke's law. It's as simple as that, Hooke's law. So, but instead of relating normal stresses, you are relating shear stresses and strain. So this is shear stress. This is shear strain. And this is the shear modulus. Okay? And as you remember, G is equal to E divided by what? Anybody remembers? Divided by this Sigüenza. Do you remember what do we have in the denominator here? For the simplest material, isotropic material, or the isotropic
times 1 plus and Poisson number.
Poisson ratio, yes, good memory. Poisson ratio, okay, good. So typical value for the Poisson ratio, Ms. Sigüenza, do you remember typical value for this? Or no? No? Mr. Cedeño, Jarry Cedeño, typical value for no? Typical value for no?
0.3.
Yes, it's about that, okay? For the steel, it's a good number. In the cases of the aluminum, which is the other material that we use, is 0.33 or so, but yeah, 0.3, it's a good approximation, okay? But if you know the exact value, use it. Okay, let's go on. Now, this is the situation, okay? We have two terms. So what we're going to assume is that the dv dx, okay, since this is a long, okay, beam in general, this is x. And in the vertical direction, we measure the deflection, okay? This deflection is small. So this is slope, this is dv dx. So we consider this is small, okay? So we simply say this is small and we can neglect. If we neglect, then this, then we have du dy is equal to simply this. But now, from chapter 2.2, okay, we know that this is the expression that we deduce for the shear stress. So this is shear force, Q, I, and B. And of course, now we have to divide it by G. Okay, so this is the situation, right? We have this is tau, this is tau. Let's suppose that this is x-axis and this is y-axis. Okay, so this is tau xy. Okay, and this is tau yx. And you see that if they are positive, they try to, this end moves axially. Okay, so this is u displacement. Okay, so because of this, the presence of tau, we have that this corner moves in the x direction. Okay, and that's the origin of these calculations. Okay, how can we calculate this? We can calculate using this expression, which employs the expression that we just deduced in 2.2. Now, if we want to calculate u, then what we have to integrate. See, integrating in y. In general, remember that the section could be, for example, formed by one element, one vertical, and one transversal element, right? We have the webs and we have the flanges. And in that case, instead of integrated in y, we have to go integrated in y and also in s or z. So we have to be a little bit flexible in this concept. And if we integrate, okay, this is the result, okay? So we have that on the section, okay, on the whole section, the V, the shear force, doesn't depend on, because it's a whole value for the whole section, one single value for the whole section. So we can take that out of the integration. Similarly, for the G, we assume that it is a constant value, so it's a uniform material beam. The inertia, again, is a single value for the whole section, so we can take that out. And we are left with this, okay? We are left with this. Okay, so this, if we take a section like this one here, okay, and we have a distribution of tau, okay, see, what we have to do is, okay, this section will deform. Let's suppose that it deforms like this. Let's suppose, okay? So originally we have straight, see, it was this. So this is parallel to that. Now we have here, this is U at S, and this is U at 0. So the distance between these two, okay, this vertical difference is evaluated with this expression. Okay, so we have to integrate from here to here. We have to integrate this term, and after this integration, this is the result. Okay, usually in some calculations, we take the zero position, the reference position, is taken at the neutral axis. That's quite common in some calculations. In other cases, what we can do is we can take the reference point, for example, in a point where we know that the shear stress is null, but we have to be careful, okay? Usually that's the way we do it, okay? Because it's quite difficult to know what position the U is 0. So we always take the difference, okay? So that's the expression that we want you to keep in your memory. Please, in this part of the course, the sign, it's going to be a very, I mean, it's going to change from expression to expression, okay? So what I suggest is you review this deduction and simply try to keep that in your memory. Okay, because the negative, the sign will be changing from expression to expression. Okay, so you are warned. Okay, so let's go on. So we have this expression to calculate the axial motion of any point of the section with relation in relative to the axial motion of another point. So we have the difference between the axial motion of 2 points. Okay, now, so let's suppose that we want to analyze this section. Okay, this beam. So this is the x-axis. Okay, in the vertical direction, this is the y and this is the z. Okay, so then the next figure, I included this because in the next figure, you're going to see that this edge, okay, separates the side, let's call the side, and this is going to be the deck. Okay, now, that's because we're thinking that this could be the section of a barge, okay, single hull barge. Now, in general, the side, we call it web, and the deck, we call it flange. Okay, so we can call both ways. Okay. Now, if we start here at the neutral axis, okay, we go up by the side, we reach the top of the side, and then we go to the left on the deck. And that's the situation when you see this this figure. Okay, so in this figure, in this direction, we have the x-axis. So it's this one here, x-axis. So we go up from the neutral axis, we go up, okay, and that would be this side. We reach the top of the side, the edge, and that's going to be this one here. Okay, this line here, this point B. And then we go up, okay, but that's this region here, which is the deck or the flange, if you want. And finally, we end up here at the center of the ship, okay? Similarly for the downward, okay? Now, because we are explaining, let me go back, we have this expression for U, okay? U is, what are the units of U, Mr. Zurita? What are the units of U? What are the units of U?
Good morning, doctor.
Units of U. But what is U, Mr. Zurita? What is U? What is U? No? Miss Aviles, what is U? Miss Aviles, what is U? No, let me go to the next, somebody else. Mr. Kimi, Andres Kimi, what is U? Mr. Kimi, what is U?
I don't know, doctor. Sorry.
No, okay. Mr. Ortega, Andres Ortega, what is U, little U, that you see here?
Length.
Has units of length, yes. It's the axial displacement, okay? So if it is axial displacement, then it must have units of length. Thank you. So we have to be careful because we need to use U in order to calculate something else, which is the strain. Okay, now, let's suppose that we have the section A, B, C, D, E. That's one cut, one section, right? Now, because of the shear stress, that's the only stress that we are considering, the shear stress, okay? Let's suppose that we have a distribution of U, okay? So let's calculate the U, applying the previous formula. Let's calculate U in the section, right? In the section. So in all of this section, let me change so we can see what I'm trying to. Okay, so right now we are here, from here to here. This is a section about here. Okay, now, because we have this shear stress, we have this axial displacement. And as Mr. Ortega said, this has units of length, okay? So this is, it's not going to be large, okay? This is going to be millimeters and multiplied by 10 to the minus something, right? This is what happens in here, okay? And this is continuous. If you go up on the side, and then you go to the right on the deck, you continue like this. There's not going to be a jump here, because if you have a jump here, that means that the material has broken. And you see that the beam doesn't break, yes. Okay, now, let's analyze another section located a distance dx from the previous one. So this is a different section. So we were originally here, and now let's suppose that we take this cut. And we have something similar, okay? And this is because the shear stress. Now comes the problem. If we take a fiber located at the distance y or s, okay? This fiber moves axially a distance u. But in the next section, the same fiber moves a different amount, okay? So if you have different amount, that means that this fiber in general has elongated, okay? Elongates if du dx is positive. If this is negative, then this shortens, okay? It's compressed. But now, in general, let's suppose that this is positive, okay? And this du dx, you know, what is du dx, Miss Leon? What is du dx, Miss Leon? What is du dx?
It's the
du dx.
the little distance that moves.
It has a very definite name. Mr. Mendez, Eitel Mendez, what's du dx?
Is another axial displacement?
No. It has a very specific name. Don't remember?
Deformation?
Strain. That's the strain, the du dx, okay? This is the strain. Okay, this is the normal strain. Okay, here I have du dy. We have to be careful. And this is the shear strain. Okay, here I have du dx. And this is the cause, because this fiber, the original length was dx, and now it has elongated. And this is the strain. Okay, but the strain, we can multiply by E, and we get, if we multiply du dx times E, what do we get? Mis puertas. What do we get if we multiply du dx by E? What do we get, mis puertas? Mis puertas, are you there?
The UDX is the normal strength and the U is
Exactly,
the
normal.
axial displacement.
If you multiply this by E, the Young modulus, what do you obtain? If you
The
multiply
normal strength.
the normal stress, yes, the normal stress. And this is, you see, the title of this subchapter. So we have U, we are going to differentiate with respect to X, multiply by E, and this is what we obtain. Okay, so let's do it. Okay, so this is U from the previous slide. Let me go. So this is U. And what we are going to do is we're going to differentiate this with respect to X. Okay, this is this. And you see that this is, I took the G, okay, outside the integral because this is constant. And the rest is, this is du dx. And this is epsilon x. If we multiply by E, this is what we obtain. Okay. This CC here in the denominator, in the subindex, it's in Spanish, corrección por corte, shear correction. Okay, that's the way we are going to call it by now. Okay, so here, is there anything that recognizes immediately the differentiation of this with respect to X? Mr. Aizaga, do you recognize? something that caught your attention, this differentiation of x in here? Mr. Aizaga, do you recognize that?
The change of the variable.
No, no. Mr. Vanegas, do you recognize anything here? The differentiation of x in here with respect to these terms? Any? Mr. Vanegas, are you there, Mr. Vanegas? No?
Is the shear stress?
No, no. The differentiation.
That is bx.
Exactly. dv dx what is equal to what? dv dx is equal to
Is
the
equal to
differentiation.
bx.
Minus moment.
Minus? No, no, no. Minus
Charge. Load.
the loading. Yes. And from where you get this, Ms. Santos? From where you get this expression? Do you remember?
The first equation of the
The keyword in this class, the keyword, everything has to be in equilibrium. Okay, that comes from the vertical equilibrium of forces. Okay, let's go on. Now, so we can identify that the derivative of v with respect to x is equal to minus p. Now, what else? Well, the inertia is a constant, so we can take that out of the integration and doesn't depend on the differentiation, so we have it here. So that's the result. So with this expression, we can calculate the shear influence, which produces a change in the normal stress distribution that we had. Okay, and that's what we were looking for, right? So that's the result. So it's minus E over GI P of X, Okay. Questions about so far? Questions so far? As I said before, you see that you have a negative here. So we have to be careful with that. Okay. So
what happened with the U at 0?
I'm sorry, say that again. Say that again, please.
What happened with U at 0 when you replace at the
This is a
normal
constant.
stress?
This is a constant. So if you differentiate this is du dx and this is 0 because it's a constant. When you integrate, remember, you can put this on the other side, on the right-hand side. It's a constant. So when you differentiate, the constant disappears. The derivative of a constant is 0. Okay. Anything else? Any other questions? Okay. Let's go on now. Now we have a problem here, and you will see that. Remember that when we developed the formula for the normal stress in pure bending, we said it's equal to minus the moment times y and divided by, anybody remembers? Sigma x is equal to minus moment y divided by, Mr. Medina, do you remember? Divided by, Mr. Medina, do you remember? Normal stress m y divided by, Mr. Medina? No? Mr.
The
Carranza?
inertia.
The inertia, exactly, divided by the inertia. Please try to be patient, okay, because I need everybody to participate. So when I ask somebody, wait a little bit until he or she answers, okay, so everybody can participate. Okay, so yes, so we have this distribution of stress, and that distribution of stress integrated gave you 0 as a net force because there is no force in the axial direction. But its first moment, you recuperate exactly the value of the bending moment. Okay? But now you are saying that you include something extra, some extra normal stress. What's the result? If you integrate the combination of sigma x plus sigma x is z, you integrate the first moment and you are not going to obtain the moment. So we have problems with equilibrium. So this is where the name Taylor appears. You'll see that in a minute, okay? So this is the situation, right? This is the stress, the normal stress, according to pure bending theory, okay? This is from pure bending. Okay, this is pure bending. So this is chapter 1. Okay, and now we have reduced this in chapter 2. So this is sigma x cc. Okay, right now, if you integrate this, okay, you integrate this minus y sigma x in general, okay, dA. Okay, you put this into here. If you integrate the first expression, you get moment, okay, you get moment. But if you put also this in here, you integrate and obtain something different. And the problem is that you have to have the moment here because that's what you need for equilibrium. So this thing here is causing us some disequilibrium, imbalance in moment. So we need to do something, okay? And then a long time ago, this engineer, Taylor, he presented an idea. He proposed an idea in order to try to complete this calculation, okay? Because right now we are in a problem, definitely, okay? I insist, if you integrate the first term, okay, from pure bending, you integrate this from pure bending, you put it into here, you see that I have I have y squared dA, that's inertia. You can cancel with this one and you get moment. But if you include also this, the second term in sigma, that will produce something extra. And that prevents from satisfying equilibrium. What Taylor proposed, okay, I did an effort in order to get the original work from Engineer Taylor, okay? If somebody is interested, I can share with this person the article, see, because I bought it through internet. It was just cheap because it's a very old article, but that's the original one, okay? It's called The Theory of Longitudinal Bending of Ships, and this is the name of the author. And you see that it's a graduate member, so probably it's an engineer with a lot of experience, okay? And he says that this paper amplified the m/I equal to f/y. What is this expression, people? What do you think is this expression? What is f in this expression? What is f? What is f? Ms. Flores? You can compare this expression with this.
Maybe the load, doctor?
No,
stress.
The stress is the stress. So you put y on the other side and you get my/I. So he's saying that he's going to alter, to change this expression, which is this one here, okay? Considering account the shear strengths, which usually we neglect, okay? So he's going to consider that. So he's going to obtain an additional deflection of the ship, and also there's going to be some changes, shrinking of the stress in certain parts of the structure, and especially in the connection between vertical elements where the shear stresses are very high with the horizontal with the flanges, where in general, shear stresses are not that important, okay? So that's the original work. And this is what he did, okay? He recognizes that if you integrate this, the correction, you are going to obtain a delta M. But the problem with this delta M is this take us out of the equilibrium, right? If you take just the first part, this part here, you integrate, you obtain the moment. But if you include this, the result is going to be some delta M, and this delta M is take us away from equilibrium, okay? So he's going to propose something. Okay, now let's suppose that we are able to calculate this delta M, okay? So this delta M is equal to, as we said here, this is chapter 1, okay? This is the normal stress times dA, that's force, and we take an arm Y, okay? But in the upper position, according to this is what we are doing. Okay, this is X. If we go, this is Y. This is going to be sigma X dA, right? So this is a little force, a differential force. And we take the arm, which is Y, will produce a negative moment because this is a positive phase. And we go like this for the positive bending moment. That's why we need this negative here, okay? So what we do is we take the expression that we just used in the previous slide, we replace it into here and integrate, and this is what we have, okay? This is what we have, okay? And this is the exact amount of bending moment which is preventing us from satisfying equilibrium. So what Taylor proposed, okay? So if we have to go back to equilibrium, he proposed to add another term, okay, in the original distribution that we have here, okay? Here I have 1, this is pure bending, 2, this is a correction, and we need to add something so that if we take the 3 terms, and integrate it here, we have to recuperate only this, okay? Now, we have calculated and determined that if we integrate this, the net moment that we obtain is delta M. So what Taylor proposed, this is just by instinct, I would call it, engineering instinct. He said, okay, let's apply a similar term as this one here. Instead of moment, we apply the delta, the difference that is preventing us from equilibrium, but with a negative sign. So when you integrate the 3 terms, you are going to have exactly the moment that we need. And that's Taylor's procedure, okay? So this is his proposal, and it's well accepted at least for quick calculation. So this is pure bending. So this is shear correction, and this is equilibrium, Taylor correction. Okay, so what do we have here is that if we have the first one here, see, let's suppose I have a bending moment here. So you have a bending moment here, what happens is that we obtain a normal stress distribution as this one. Okay, here I have compression, and here I have tension, and this is sigma X of Y. So this is the first term. Now, we are saying that because the shear that causes some axial axial displacement, we have another distribution of shear stress, or normal stress, I'm sorry. So we have the same section, and we're going to consider this. So we're going to have some, let's suppose that we have something like this. Okay, let's suppose that here I have positive. I have here negative. Okay, and if we integrate this, we're going to get some delta M. Okay, so delta M is the integration of the first moment of this stress. But the problem is that this is what we need, because here I have P of X. This is P of X. This is what we need for equilibrium. If we apply this, then we're in trouble. And this is what Mr. Taylor, Engineer Taylor proposed. So I'm going to change color with green. And this is what he proposed. Okay, so he said, okay, let's take the same section. Okay, but we need a distribution of stress which opposes this one here. Okay, so this is what he did. He proposed a linear distribution, but with opposite signs. So it's going to be like this. And here it's going to be like this. If you integrate this, you obtain this delta M. If you add the three effects, what happens? That the second and the third cancel each other. And eventually, you are going to obtain the bending moment. So this term here and this term here cancel out. And this is going to be the net, the net moment is going to be the moment that we need, right? But these distributions produces something which take us away from the original normal stress distribution that we calculated using the kinematic hypothesis, okay? In here, as I said before, we have to be careful with the signs, okay? With the signs, okay? So you see that this negative here, okay, that's from the original deduction, chapter 1. This negative comes from the derivative dv dx equal to minus p of x. This negative here is basically the same as this one here. It's the same, okay? Because that's what Taylor proposed, right? To assume that there's going to be a distribution of normal stress in order to bring the section back to equilibrium. But since we need to produce a negative delta M, what we have to do is we have to add a negative. So we have to subtract. And this is what we have here. That's why we need this negative. So we have one negative and one negative. So we have to be very careful with the negative signs here. Okay? So this is the expression that we can use in order to obtain the redistribution of normal stress on a section. Is there any questions about these, people? Any questions about this so far? What I suggest is you try to do this procedure, okay, in a very graphical way in order to try to understand, okay, the procedure, and then try to remember some of the details in this development, okay? After doing this, we need to do exercises or examples if you want, okay? So right now, I'm going to start, just before the break, we're going to start the simplest case. The simplest case is to apply this to a flat bar, okay? And then next session, tomorrow, we will be able to apply this to a more complex section. And this example, you have it in your class notes. Both examples are in your class notes. Okay, so let's do it. So we have three expressions. One is for the normal stress following pure bending. The other one comes from the fact that the shear strain produces some axial distortion of the section, and that produces a change in normal stress. And the last one, it comes from Taylor's theory, saying that we need to, when we integrate the full expression, we need to recuperate the bending moment on the section. And that's the last one here, okay? So let's complete this part by starting the example, okay? So this is the flat bar, okay? In Spanish, flat bar means, anybody? Do you know the translation of flat bar in Spanish? Anybody, please? Remember the translation of flat bar, anybody?
Latina.
Latina, exactly. Okay, so it's a good idea that you remember these terms, okay? So we're going to analyze a Latina. I'm going to write it here so you can start getting ready for your work, okay? So it's like having something like this. There, okay? So I'm using this B symbol, but you know that this is the thickness, okay? And of course, this is the height of the flat bar. So for the flat bar, you need only two parameters, height and thickness. And let's suppose that it is steel, okay? So since we are going to calculate the shear stress distribution, we need the first moment. Remember, this is something that I insisted in class, okay? We have the x-axis here, have the vertical y-axis here, and we said that we make a cut and we define the sector. And the sector starts at the point where you want to calculate the shear stress, and you have to end up here. What is the shear stress up here? What is the shear stress here? This is tau yx. How much is tau yx up here? Mr. Yanis, what is tau yx up here? Mr. Yanis.
Good morning, doctor. Tau is 0.
Exactly. It's 0 because it's open. So there's nothing above it to produce any shear. So tau there is 0. So you integrate from y and you go all the way up until the free end, where you know that free edge, where you know that the shear stress is 0. So you have one expression and one unknown, which is tau in the point y. Okay, so that's basic concept that we started explaining at the beginning of this chapter. Okay, now this is the expression that we have to satisfy. Okay, we have three terms here. This is 1, this is 2, and this is the Taylor correction. Okay, so we have pure bending, shear correction, Taylor correction, and this Taylor correction comes simply from the fact that we need to recuperate the bending moment if we integrate the first moment of the normal stress. Okay, so let's go. Well, this is very easy. This term is a little bit more complex. Okay, so we need to start by Q. What is Q? How do you calculate Q? Mr. Villalba, how do you calculate Q? Large Q?
The area of the section.
Not the section, not the area of the section, the area of the sector.
Sector.
Okay, yes. So it's the area where the half crossed here. That's the sector. Okay, so this is the sector. This is the sector. So it's the area of the sector multiplied by
centroid.
Multiplied by the position of the centroid measured from the neutral axis. Okay, now here we have the basic definition. So this is the integration in the sector. Okay, this is the first moment. Okay, now dA, we can take a little piece here. This is dA, and it's equal to B times dy. Okay, And for this little sector, we know that the centroid is uniform is equal to y. Okay, so we take the B outside because it's the thickness of the flat bar is uniform. Take that, and that's the result. And we have done this previously. So we y squared over 2 upper limit, which is half minus y squared. And we can recognize that when y is 0 on the neutral axis, we have the largest value of the first moment. Okay? So please, we have to be careful because we are starting here and we go all the way from here to here. Okay? So that's Q. But in this case, we need to integrate Q dy divided by B. Okay? Now, let me go back to recall where did we introduce this expression. Let me go back. Okay? So it's today's lecture here. Okay? Okay, here. We said that, oh shoot, sorry. We said that after obtaining du dy, we integrate, okay, from a reference point and up to a certain section from the reference point. In this case, in this flat bar case, we are going to take the reference point at the neutral axis. So this integration here, Q ds over B, so this integration will be from the neutral axis and up to the section where we want to analyze. Okay, so we go here. Okay. So this term here that we see Q, I wanted to insist on this because we can get confused. This term here, we just review that this integration goes from the reference point, okay, and the reference point we're going to take at the neutral axis, okay, and we integrate until a certain any point here, okay, and this point here will give you the shear, the normal stress at that point, okay? So this in general has to be a function of y, okay? So this integration goes from 0 to y, okay? And y could be any point in the height of the flat bar, okay? So the integral goes from here until here. And at this point, this is the result of Q. So this that dy and 1 over B because we have B down here. So we can cancel this. This is the integration in y. So the result is going to be this. And this is going to be the integral of this expression. You see here that this is not a constant, okay? Because we are not integrated over the whole section. We are integrated up to or from the neutral axis and up to any point where we want to analyze, okay? So this is why we say this is a value, this is a function of y, okay? This is something that I insisted in previous maybe you want to correct this in your class notes. This, maybe we should put it as this depends on y. This term, this function is the integral, and it depends on y. Let me correct that in my class notes too. Okay, so let's take a break here. Let's take a break here, and let's take a 5-minute break. And when we continue, we will be trying to evaluate the other term, the delta M, and finally put the whole thing together and see what do we obtain, okay? So let's take a 5-minute break. I will ask, I will ask Miss Sayo to stop the recording.
Okay, doctor.
Okay,